Alaikum and good afternoon everyone. So from the title, what I'm talking about is combinatorics and subdivision operation, which means that so I'm talking about combinatorics which are associated to geometric objects, and especially the effect of the combinatorics under the subdivision operations. So here is the overview of my talk. So it's divided in these parts. Firstly, I will talk about what are the geometric objects which I'm talking about. These are simplicial complexes, and then I will talk about what are the combinatorics which are associated to these associated to them, and then I will talk about the subdivisions of simplicial complexes. So you know that this most of the topologists and geometrists, they know that the subdivision is a very important tool to study the manifolds or some other geometrical objects, especially the topological spaces. And then we will talk about the Eulerian polynomial, which is a part of algebraic combinatorics, and it encodes the some statistics of the permutation groups like an. Also we'll talk about the more generally the permutations of signed permutation, right? And at the end we will see that how what we have defined before, these objects are related, how they are related to each other, how what is the connection between these objects. Okay, so let's start with the simplicial complex. Here I'm giving, first of all, the geometric definition of the simplicial complex, which is just a finite collection of geometric simplices. So simplices are just the convex hull of some vertices which are finally independent in Rk. So a d-dimensional simplex is just coming from the convex hull of d plus 1 vertices. So for example, here are the vertices of dimension 0, which is just is a simplex of dimension 0, which is just a vertex. And this is an edge, which is one-dimensional simplex. Here is triangle is a two-dimensional simplex, and this is the three-dimensional simplex, which is a tetrahedron. And I will also say something more. If you will consider here some simplex, and if you will consider here some simplex, which is a subset of this bigger simplex of dimension less or equal to that one, that is called a face. For example, in this tetrahedron, this triangle is called this triangle is a face. These edges are faces, and these vertices are faces of this simplex. Okay, so simplicial complex is consisting of finite collection of these geometric simplices, but how they are joined or they are placed in the in Rk, which is a Euclidean space. So if you are picking two simplices from this collection, then their intersection is either empty or just a face of both P and Q, which means that the intersection must be a face of both P and Q, which means that we are not allowing such pictures in our simplicial complex. So for example, here in the first picture, you can see that the intersection is just a point, which is a vertex, which is a face of the below triangle, but is not a face, which is not a vertex or of the above one. And in the second picture here, are again the intersection is a line, and it is not a face of both of them, right? So we are not allowing such situations in our simplicial complex. And the other property is that if you have a simplex in your collection, then if P is a face of that one, then P must be a part of that collection, which means that P also be a simplex in this simplicial complex, which means that if you have this triangle in this delta, which is a simplicial complex, then we must have these edges and vertices must be a part of delta. But if you have this triangle, but you are not including this edge, then this means that this is not a simplicial complex. So this is the definition as any simplex which is an element which is here, that is actually called a face of simplicial complex, right? And the dimension of this simplicial complex is just the maximum of the dimension of the face. Yes, face, which is in this. So here you are just considering the simplicial simplex, which is the high maximum of maximum dimension. That dimension is also the dimension of the simplicial complex. And now what I will do, I will define the abstract simplicial complex, which means that because sometimes we need to define specific situation. In specific situation, we need sometimes geometric one, and in other way, we also need sometimes abstract one. So that's why I'm defining these two notions. In an abstract simplicial complex on a finite vertex set is just a collection of subsets of V, such that each singletons, they must be a part of this simplicial complex. And if you are taking F, which is a some subset here, and if E is any subset of this F, then E must be a part of this simplicial complex, right? With these two conditions, so here I will again define the element. Any element in this collection is called a face of this one, and the dimension of this gamma is just the maximum of the cardinality of F minus 1, which is actually the dimension of the face. So the dimension of face is just the cardinality of that face minus 1, right? And now what is so these two definitions are here. Now we will see that there is, you can go from one side to another side, and if you have some geometric simplicial complex, then you can easily form a abstract simplicial complex from the geometric one. How? So if you will consider simple the simplex from this, or face from this geometric one, you will just translate you will just consider the vertices of that simplex, and you will construct the abstract simplicial complex. So for every face or a simplex here, you will get just a subset of bigger V, which is just a collection of all vertices in this delta. So you get in this way gamma. And if you have a gamma, then what you will do, you will consider Euclidean space, which is of dimension V. The number, the cardinality of V is, let's suppose, B. So you will just considering the corresponding to each vertices, you will just consider the basis unit vectors. And what you will do, you will consider a face here, for example, F, then you will consider just the convex hull of that elements which are contained in this F. So in this way, you will just get this geometric simplicial complex. So now we are free to move from abstract simplicial complex to the geometric simplicial complex as well. Okay, now what we will do, we will define what are the combinatorics which are associated to a simplicial complex. And what we will do, we'll just count the number of faces of dimension I minus 1, which I denoted here Fi, and we will consider this vector which just say the number of faces in each dimension. And so the associated polynomial which just gives you these F vector is called the F polynomial of this simplicial complex. And there is another vector which we will associate to this delta. It's called H vector, and H vector is coming from this H polynomial, where H polynomial is defined, is interlinked with this phase of F polynomial. And you can see that how this H polynomial is linked with that this one. So H vector is just image of this F vector under some linear transformation and nothing else. Okay, so this is F vector and H vector, and you can see that F and H gives you the same information about the object, about the simplicial complex. They have the same information. If you have F vector, you can find the H vector, and if you have H vector, you go back to the F vector. Okay, here you can see example, and we can calculate the F and H polynomials here. Okay, so you have this simplicial complex. You can see that this is not shaded, which means that this is not a two-dimensional simplex. I mean, if you're considering just these 3 points, these are just edges. This is not a two-dimensional thing. And here you have, okay, let's count what are the number of vertices are here. So you can see that here number of vertices are 6 number of vertices, and there are edges which are, how many edges are there? 11
10,
edges.
10,
Sorry, 10, right. Okay, and
4,
then
4, 8 to 10.
10.
Yes, 10.
Okay, thank you. And number of faces of dimension 2.
4.
4. Okay. So what we get? We get this f polynomial here. So 1 is number of just vertices. So here I just need to mention here f0 is the face of dimension -1, which means that the empty set. Empty set here is just 1. So that's why we will always count here this as a 1. Okay. And then by using this formula, which is here, which is just, you can also calculate by the linear transformation, you get h is this one. So 1 plus 3t plus t square minus t cube. Okay. So here you can see, you can easily observe that this f vector is always integers, non-negative integers. But here h can be uh, uh, can be integer, either positive or negative. For example, from this example you can easily see that it could be some negative terms could be appear in h vector. Okay, so
Dr. Shaheen, there's a question in the message inbox.
okay, let me
So,
see
how cardinality of a face is defined?
how the cardinality of.
A face is defined.
Okay, so if you are, okay, there are two different definitions. If you are considering here the geometric one or the sorry, or the abstract. So abstract में जो है, in the abstract there is f which is just a subset of v.
Hmm.
So it's just a cardinality of f. How many numbers or how many elements are there in f is a cardinality of f. So this cardinality and -1, why we have associated, you can see that when I have connected, I have defined this connection from abstract and geometric one. So you can see that if you have 4 points, for example, and you have connected there in 4 points with the 4 basis vector in unit vectors in some Euclidean space, then what you will get? You will get a simplex of dimension 3. So their size dimension is 1 less.
Okay, and then there is another question by Sabah, and she's asking why we need each vector when we can have the same information from the f vector.
Yes, I'm coming to that point. Okay. So after this example, I'm going to say something about the motivation why we are studying this h vector when both are giving the same information. But
One more question.
yes,
Excuse me. I have one more question. What is the domain for t, the polynomial? In f polynomial or h polynomial. So there is a question: what is the domain of t?
domain of the polynomial. Here you can see that the domain is a set of integers.
Okay.
So these polynomials are lying in Z of t, the polynomial ring with the integral coefficients. Okay. Okay. Any
Okay.
other question?
Basically, we are formulating the polynomial in variable t. So it is
Yes.
it can be considered as a polynomial function. So polynomial function can be defined on any domain,
Yes,
but we are more
it
concerned.
doesn't matter. It doesn't matter because, but if you are looking the coefficients, then you can easily see that what will be the domain of it. It is not necessary to be precise to be here to be defined that no, it's just domain is just a set of integers.
Okay, this is just for the case of studying. Okay, probably you should say it more about why these polynomials are important in the terms of generating function.
Okay, I'm coming to that point. So Okay, so the first of all, let me answer this question: why we have defined this h polynomial? When we have this f polynomial, why we need this thing? So this is the motivation to study these h vectors. Is a little bit more algebraically sense. Okay, that's why I'm not giving here too much detail about the algebra, because about in this talk I'm mostly focus on this geometry and combinatorics. So, but to give the motivation, so let me define these things. So, if you have abstract simplicial complex on some given vertex set omega, then what we will do, we will define, associate a ring to this delta, which is called the Stanley-Reisner ring, which is just just a quotient ring, where the number of variable are depending on this vertex set, and this ideal is defined in this way. You will just consider the monomials, and the monomial here you will just take the those monomials which from this n is not a phase of delta. For example, if you're just considering a boundary of a triangle, which is 1, 2, 3, let's suppose, and this is just, you are not taking the phase 1, 2, 3 as well. So what will be the known phase? Known phase is just 1, 2, 3. So the monomial in this case is just the x1, x2, x3. And that you will be quotient out by this one. So you will get this Stanley-Reisner ring. So this is the algebra which is associated to this simplicial complex. And now if we will study the Hilbert series of this simplicial complex, what we will get? The Hilbert series is nothing, just this one. And you can see that is the denominator, oh sorry, numerator is just nothing, just the h polynomial of the simplicial complex. That's why we are more interesting to study the h vectors, because h vector has the same information, but it gives you sometimes very precise answers, or many results you can see. If you will translate those things in h vector, they give you the simple answers. So that's why we are interested to study the behavior of these h vectors as well. Okay, so this is the reason. And now let's ask some questions here. Okay, so if you are given, so you know that we have some combinatorial data, which is just counting the phase vector of number of phases of the simplicial complex. So let's ask this question: if you have any arbitrary vector of positive integer, let's suppose, what is, when it is true that a is some phase vector f vector of some simplicial complex. So is it always true that if you will consider any vector of non-negative integers, then it will become a f vector of some simplicial complex or not? So this is answered by Rees, Kruskal, Kotana, and Schutzenberger. They have answered this question separately, and they have given the answer in terms of some inequality or some relation between these AIs. So I'm not giving that detail here. And then you can ask another question: when is this vector non-negative? Because you have seen here in some example, this is always not non-negative. So you can ask this question when this h vector is non-negative. So this is answered by the Stanley. So h vector of non-negative integer is always h vector, if you're considering a vector, is always a h vector of shellable simplicial complex if and only if h is Macaulay vector. Here, so this is saying something there. You get h vector non-negative only when you have this shellable simplicial complex. What is a shellable simplicial complex? Shelling is specific order of the facet. Facet is the faces of the maximum dimension. If you will order them in a very nice way, then you will get that simplicial complex is shellable. And for those simplicial complex, this h vector is always non-negative. And moreover, there is another condition which is saying here H is a Macaulay vector. This is a condition which is connecting to the algebra, or you can say that which I have already said something about here in this part. So it's mostly connected to this algebra. So I'm not talking about that one. Or you can say that this is giving you some specific relation between these HIs. Okay. So let's move to another question. This question is saying that what are possible number of faces of different dimensions of a simplicial sphere? Here I'm saying something about the simplicial sphere is a simplicial complex which is homeomorphic to the sphere, right? And this question was asked by the Peter McMullen, and in 1971, if you will consider this simplicial complex, then can you count the number of faces of different dimensions? And there are the answer of this question, which is the McMullen G conjecture. Is called the G conjecture, and a sequence is saying that is a sequence of non-negative integers is a f vector of d minus one dimensional simplicial homology sphere. And I will tell you why I have written here this simplicial homology sphere, because at the beginning McMullen asked this question for the simplicial sphere, not for the simplicial sphere, but for the simplicial polytopes, which is general terminology from this simplicial complex. If and only if you have following relations, hi is same as hd I minus 1, which is saying that h vector is just, or h vector, if you will consider as a vector, is a symmetric one, right? And these are called the Den-Sommerwille equations. Actually, these equations, Den-Sommerwille equations, are actually the complete list of relation of the face numbers of simplicial complex, or more generally simplicial polytopes. So this gives this complete list of relations. But when you, in terms of FIs, but if you will translate these equations in terms of HIs, you get just this nice relation. HI is equal to HD minus 1. So this is another motivation to study these HIs, because in this situation, you can easily see that what are the relation between FIs, and you can just translate in HIs. Okay, if you will consider GI, which is HI minus 1, and this is always non-negative, right? The third condition is saying that this G is, which is just this G1 up to GD by 2, is a Macaulay vector, which means Macaulay vector, I just add a remark here. Macaulay vector is also saying that this vector is actually a f vector of some simplicial complex, or more generally multi-simplicial complex. Okay, so the McMullen asked this question first of all for the simplicial polytopes, and that was answered by the sufficient conditions were answered by the Billa and Lee, and then Stanley proved the necessary condition for this one. And later McMullen also gave the proof of this conjecture, and this conjecture was very open for the other spaces. For I mean, if you are not talking about the simplicial polytopes, but in general you are talking about the simplicial sphere, or more generally if you are talking about the simplicial homology sphere, then the problem was open like 30 or 20, more than 30 years. But recently, this conjecture is proved more generally for the simplicial homology spheres by the Adai Presito in 2018. Right? That's why I have written this conjecture for the simplicial homology sphere, because it is now it is a theorem for these spheres. Okay.
So
Yes.
Shaheen, this is proven general for, it is proven general now.
Yes, it is proof. Now it is proof for the simplicial homology spheres.
Okay, so for which cases it is open? So there are shellable simplicial complexes which are not simplicial homology sphere.
No, they are shellable is here. because
Mm-hmm.
shellable simplicial complex is just nothing, just the wedge sum of spheres.
Mm-hmm.
So that's why
Okay.
they are covered here.
Okay. And hmm. So now what is open?
It's
What is open then? This is open
uh,
for
if something which is not simplicial homology sphere, for those one, this is
then.
open. Yes, then it is open.
Ah, okay, okay, okay.
Okay, so let me remark here the proof of this conjecture is which given by the Adai Presito recently like two years ago this is based on very strong geometric and combinatorics arguments like Hodge theory and very complicated complex geometry of convex geometry, right? So let's, okay, any question so far?
Um, okay, there is one question in
Yes,
the message box. Does we can define the facet ring parallel to non-facet Stanley-Reisner ring?
yes, we can define, because here we are in Stanley Reisner ring, we are just considering the non-faces, and if you want to study the facet ideal or facet ring, you can just consider, instead of non-faces, you can just consider the facet one.
Yeah. Okay. So in parallel, there is a study.
Yeah,
There are
yes,
different studies
there
which
is
are.
a study, but as I said before, I'm not going too much detail for the algebraic part. So that's
Hmm.
why I'm not connecting these things in with the algebraic properties of the simplicial complex, either in for the Stanley Reisner or you are studying for the facet one. Okay.
Okay. I think move on.
Okay, so now let me go for the subdivisions. So here I'm just talking about this geometric subdivision. So you know that the subdivision is a very important tool, and these study is starting from the Stanley's paper. He asked a question that if you have this H vector and if you will just subdivide your simplicial complex, what will be the effect on this H vector? And to answer this question, he has a lot of he has defined various subdivisions, but here I'm just picking this geometric one because my results are mainly focused on these ones, so that's why I'm just talking about these geometric subdivisions. So if you have two geometric simplicial complex, so now here I am taking geometric definition for the simplicial complexes, and one of them is called the geometric subdivision of the other one if every simplex in the subdivision is contained in some simplex of the original one, and every simplex from the original one is a union of the simplices from the subdivision. So this is the definition, and to see what definition is saying, so for example, if you have this simplicial complex, and this is what I'm saying, that this is some subdivision. So you can see that if you will consider a face here in this subdivision, this face is a part of this face or a simplex in this one. And if you will consider a simplex here, either a one dimensional or this two dimensional, this two dimensional is just the union of these three simplices in this subdivision. And if you will consider that this edge is just the union of these two edges in this subdivision, and so on and so forth. So here I have just posed this geometric subdivision. There are a lot of other kind of subdivisions, but I'm just talking about this geometric subdivision here. Okay, and now let's move on this barycentric subdivision, which is a more geometric one. But here I have written this definition in terms of the abstract simplicial complex. So if you are considering an abstract simplicial complex with vertex set V, then the barycentric subdivision is a simplicial complex on this vertex X, which is just the non-empty faces of this simplicial complex, with the simplices are just the chains in this one. So you can see that you can consider the barycentric subdomain is the order complex of the poset, which is just which are just the non empty faces of delta. So this, what I'm saying that this k length chain is giving you a k dimensional face in this barycentric subdomain. And you can also consider the geometric one. If you are considering the geometric, why it is called the barycentric here. If you are considering the geometric simplicial complex, then you can, what you can do, you can just consider the barycenters of each faces in that one. For example, if you have a triangle, two-dimensional simplex, and if you want to consider the barycenters of these triangles, you can see that for the single vertices, the barycenters, they are by themselves. And if you are considering the edge, then you have a point on the edge. On each edge, you have one more point, right? And for the two-dimensional, or you are considering one, two, three, all of three, or this, sorry, two-dimensional phase, then this is one, two, three. Those, so the barycenter means that you get a one point in this simplex of two-dimensional space. And how they are linked, I mean, how they are connecting, which these one, they are connecting this way. So for example, this is a barycenter and this is a barycenter. We will connect this one in the way the corresponding faces, they must have this relation. One is contained in the other one. So for example, I cannot connect the one with two, because one, this is the corresponding face is one, its corresponding face is two, and one, two are not connecting. And similarly, you can see that one is connecting with one, two, three, one, two, and one, three. And this is two-dimensional face because you have this chain 1, 1, 3, and 1, 2, 3, right? So the corresponding to each barycenter, you have this what you call simplex. This is a simplex corresponding to these barycenter, corresponding to this chain, which is 1, 1, 2, 1, 3, and 1, 2, 3. So for the rest is the same, similar one. Okay. So now so this is the very geometric and very well known, very well studied barycentric subdivision from all aspects in various fields. You will see this barycentric subdivision. Okay, now I will move on to this interval subdivision. So the interval subdivision, let me just quickly define what is an interval subdivision. This is introduced by actually the Walker, and this is just an order complex of this poset. Poset, you are considering just the closed interval which are satisfying this relation. A1 is a subset of A2 if you are considering these two faces in delta, and you have this relation. I mean, how they what is the order for this poset is defined in this way. It's just the inclusion of these nested intervals, right? And let's see this example. If you have this two simplex, and you will just take this interval subdivision of this one. So you are just considering here, if this is one, here is 1, 1. I will just pick 1, 2, and 1. Oh, sorry, 1, 1. This is 2, 2, 3, 3, and here is 1, 1, 3, and so on. You will just fill out by these numbers. But it is the interval subdivision of this two simplex. Okay. So what is our goal here? What is, this is the combinatorial. Yes,
Shaheen,
yes, yes.
Can you give a particular example of an interval from your previous examples to formulate how the interval come up?
How the interval come up? So here we are
Or
just
probably the people are not aware with the terminology of interval.
okay.
In simplicial
As I said, closed interval. Why it is a closed interval? Because you are just picking, like the interval, you are just taking two elements from this simplicial complex. That's why it's called we call is interval subdivision, right? And the relation, I mean, how they are ordered. We have some order between them. This is clear from here. You have this order relation. We say that this is a subset of, or you can say that the order with this B1 and B2 if you have this relation. So B1 is contained in A1, A1 is contained in A2, and A2 is contained in B2. Right?
Can we go back to
Relation.
the particular example from the picture you have already mentioned? Example, the example you explained regarding to simplicial complexes, to just see
Okay.
formulate various intervals. Just
Okay. So here, this picture is for the two-dimensional simplex. But if you will go back to the original one, you can do this thing for each simplex. You can apply this thing for each simplex. If you have some simplicial complex, which is like here is some in triangle, then you can just let me just draw if I can. So for example, if you have something here.
May I say something? Excuse me,
Yes,
ma'am.
yes, yes, yes.
yes, Fariha, bolo.
Ma'am, why don't you use your paper on interval subdivision? It has a better labeling there.
Yes,
It
I
is
know that.
very,
I know
yeah.
that there is some labeling, but I don't want to spend so much time to just doing on this because I have a lot of stuff to talk about, right?
Okay, okay.
If you are
Okay,
really interested, you can ask in the answer question session. Then I can
okay,
show
okay,
you
okay.
on the
Continue,
paper if
continue.
you are interested.
Okay, thank you.
Okay. Okay. So let's move
Okay,
on.
Shaheen, there is another question. What is the basic difference between the interval subdivision and barycentric subdivision?
What is the difference? I think
Hmm.
it's a very clear difference from the picture. So this is
Hmm.
one particular subdivision, and this is another subdivision. Right, there is no relation, but if you will just consider that this is the same one, if I will just consider here what I should say, that if I will just consider just the closed intervals which have the same endpoints, then you will go back to that barycentric subdivision, right? If you'll just consider those one, not considering like a 1 and 1 2, if you will just consider 1 1, then you will get the same barycentric subdivision from this one. So it is something more general than that one. Okay, so
Okay.
let's move on. So what is our goal here? Our goal is to study the behavior of these f vector and the h vector, either of them. If we'll replace this delta is by the geometric subdivision. So we are interested to ask these questions. What is the linear transformation from this vector, face vector, to this one? And similarly for the question for the h vector. So one can ask this question again, if this linear transformation is consisting of the positive integers, and what we can say about those positive integers. I mean, can we give a combinatorial description of these coefficients? This is the basic or fundamental question in the algebraic combinatorics. If you have some interesting sequence of non-negative integers from some geometric object, then this is the fundamental question to ask about what are the combinatorial description of these coefficients or these vectors, right? Okay, so let's move on. So we want to study this one. So I'll just give you some examples for d equal to 2. If you will consider for d equal to 2, what you will get, you get this transformation is this one. You can see that maybe it's a diagonal one. No, it is not diagonal. Yes, but it has some. If you will go further for d equal to 3, then you can see that this is this one. But from here you can see once you can notice that the first row is the same as the last row in the reverse order, and this is the same true for the second row and with the third row. And this is something interesting property which are coming from here, and this is for the barycentric subdivision. This is something which is already known, and what we study here is about the interval subdivisions. When we study these linear transformation, we get something like that here, which is of course from here you cannot guess what is going on, but if you will go further, you can see that you get the similar kind of properties. For example, if the first row and the last row, they have the same opposite connection, and the similar for the second and third one, and this is same also true for the columns as well, right? So this means that what was known for the barycentric, uh, can we see something the similar kind of relations or similar kind of results for these interval subdivisions or not? So to answer this question, I know I need to go to, okay, so let me give you some motivation. First of all, as I said before, if you had some sequence of positive integers, and you can take this generating polynomial from that sequence, and we'll say that this is unimodal. If it satisfies this relation, you get some peak there, you get increasing, and then you get the decreasing coefficient, log concavity, and real rootedness. If it is zero, or either you have only real roots. So this real rootedness implies the both unimodality and low connectivity. In algebraic in algebraic combinatorics, the people are mostly people are interested in these kind of relations to study about the, if you have some interesting sequence of positive numbers, what we can say about the unimodality, because these kind of things have some hidden or very interesting things about the geometrical objects. So another motivation is about the Charney-Davis conjecture, which is something more general for the more general theory. But here I have just translated this Charney-Davis conjecture for the simplicial complexes. If you have flag simplicial homological sphere of dimension d minus 1, then you have this relation, the h-polynomial. This means that the alternating sum of the h vector times this number is always positive. And this conjecture follows if you are considering these odd number. This is just follows from this one, because for the homological spheres, we have already seen that we have this symmetry relation due to the then Sommerwald equations. And for d equal to 2 is just trivial. And for d equal to 4, it was proved by Davis and Ocon. And then if you have this relation, if your polynomial is real rooted, and of the simplicial complex with the further some relation, relation about the h vector is symmetric one and non-negative, then you can say something about the Charney-Davis conjecture. This holds for the delta. So you need to, if you want to prove Charney-Davis conjecture, if you get that your polynomial is real rooted, then you have this conjecture. The conjecture holds for that, those simplicial complexes. Okay. Because as I said that if you have h polynomial real rooted, but if you don't know if your h polynomial is not real rooted, then you can definitely you can't say anything about the Charney-Davis conjecture. And that time there is a Gall's conjecture, because Gall gave an example of h polynomial which is not real rooted, and so he come with this new vector which is called the gamma vector. And it's gamma vector. How you get this gamma vector? If you have h vector which is symmetric one, then you can always translate your h vector in terms of these gamma coefficient. That's why this is called the gamma vector. And he conjectured that if you have this flag homologous sphere, then this gamma vector is non-negative. And for D, even the Charney-Davis conjecture is equivalent to the Gauss conjecture. So this gives you the more strengthened to prove, or this Davis Charney-Davis conjecture. So if someone cannot get that your polynomial is real rooted or not, then you need to study these gamma vectors. Okay, there are again very interesting question. If these are non-negative, so what are the combinatorial interpretation for these gamma vectors? So there are a lot of list of questions.
Excuse me.
Yes, yes.
Shaheen, there is a question. What is a flag simplicial homology sphere?
Okay, as I said that flag means that if you are considering the non-faces, they must be of dimension 2. Minimal non-faces are of dimension 2.
Okay,
right?
the persons who are familiar with the Stanley-Reisner theory, so all those simplicial complexes who are flagged,
no,
their Stanley-Reisner ideal is
if you are considering simple example is that if you are considering two-dimensional simplex, the boundary of two-dimensional simplex, this is not flag, because here minimal non-face is 1, 2, 3, whose cardinality is Cardinality is 3, but the dimension is 2.
Okay.
That is
There is
not
another
non-flag.
question.
And
There is
homology
another
here,
question.
I already said that it's if you will consider the it's it's more like more geometrical definition. If you will see like locally or the restriction of the simplicial simplicial complex on each face, then they must be homotopically equivalent to these pairs. That's a easy one definition. Yes,
Okay.
another.
There is another question which is quite a natural one because Chandra-Davis conjecture directly follow for when D is even.
Mhm.
So there is a question that can we say that
No,
the
when D is
Chandra-Davis
odd.
conjecture D is
Sorry,
odd?
D is odd.
D is odd. Okay. When D is not
No, for
even. Okay.
D, yeah. When D is odd, then you can easily get, because of the symmetries, you get just the sum, alternating sum, then you will just 0.
Yeah.
Okay, so okay, now let me come to this this section, which is about the algebraic combinatorics. Here we are talking about some statistic of the permutation. So let me go quickly because I am short of time. So here we are taking the permutation group. This is a symmetric group of on n, and the decent number of this permutation is the number of those i's whose corresponding sigma is greater than the sigma I plus 1. And this cardinality is called the decent number of the corresponding sigma, which is an element of our permutation. Okay, and if you have this definition, then you can come up with this classical Eulerian polynomial, or the polynomial Eulerian polynomial of type A is just encoding these data, which is these coefficients are the this is just again the generating polynomial of the permutations with the who's counting the descent numbers. So A and K is just the number of permutation in A with the exactly K descents, right? And then one can notice that an is always symmetric because of this relation, because when you have uh, something which permutation with descent k, then you can just take the another permutation which is just n plus 1 minus sigma i's. You get another permutation, and that permutation has n minus k minus 1 descents. So you have one corresponding. That's why you get this relation. And further, what we have it is done that one can refine these polynomials by putting just condition on the permutation. You are just considering this permutation whose sigma 1 is j. So in this way, you get just these polynomials. And one can observe that if you will just consider j is equal to 1, if you will consider here 1, sigma 1 is 1, then you get the classical Eulerian polynomial with one in the previous step. Okay, and we have this relation, as I said before, we have this connection. And one more interesting property which is written here, that this sequence of refined Eulerian polynomials is interlacing, which means that all polynomials are real rooted and their roots are interlaced. And this order is most important one, because you cannot choose any order, but you need to pick specific this order. Okay, there is an the similar kind of notations for the hyperoctahedral groups, which are also called the sign permutations. Here you are just considering the permutations from this set, which contains 2n elements with positive signs and with the negative sign, such that they satisfy this relation. If you want to calculate what is the sigma minus 1, it must be same as minus sigma I, right? So you can view this is S and 2, but you can also see that with this relation, you can just completely define by this first sigma 1 up to sigma n relation. So we will just focus on this one. For example, if you
Excuse
know
me.
that, yes.
What is interlaced roots of the polynomial you mentioned?
Okay, their
Yeah.
roots are interlaced means that if you are picking some roots of a and 1, and they are real rooted, then you can place in some order. And similarly, for the other polynomial, this is again real rooted, so you can place their order. So one of for let's call these are alpha i's and these are beta i's. So alpha 1 is if I will take the order alpha 1 beta 1, then alpha 2 beta 2, alpha 3 beta 3, and so on. This kind of is relation is called interlace. This means interlace. Every two for any two real roots, there must be one root from the other polynomial, and similar this is true for the other polynomial as well, right?
Okay.
Okay. So okay, here we again define this descent number. For this one here we have included this sigma 0, which is we are considering here 0. You can also define the descent number of type A, but here I'm considering here the descent number of type B, which is this one. Similarly, we have this Eulerian polynomial of type B, which is just a generating function for the number of permutations with exactly descent k. Okay, here we have similar kind of symmetric relations. And now we have defined here the Eulerian polynomial, and we have defined in terms of these way. So here we are considering the Bn plus, which means that you are fixing your last sigma n that must be positive, and B minus it is just -1. So in this way, you have divided your whole Bn in two parts, and by using that one, you have defined the refined Eulerian polynomials as we have done for the type A. And we have these nice relation, which gives us actually the interlacing properties between them. So I will discuss later. Okay, now let's come what is the connection between all these things: Eulerian polynomial, f vector, h vector, how they are connecting. So this is the beginning of the enumerative theory, the study of the enumerative theory from this point of view, and that is due to the Brenty and Welker, and they started this thing for the barycentric subdivisions, and they have just they have given this relation of f polynomials, and this I plus j, this is just the Stirling number of second time, which is just the counting of the set permutation of n element set in k parts. So if you have some set with n cardinality, if you will divide these one in k parts, I mean the partition of the set, then this how many partitions are there, this is called the Stirling number of second time. And these f vectors are f vector of these barycentric subdivisions are given by these one. So these are the coefficients which we are talking about. Can these have this nice combinatorial description? And how we get, because if you are considered k-dimensional face in this barycentric subdivision, which means you have this chain, you can translate this chain into this partition, right? And because here we are considering not the order of this one, that's why we get here this coefficient j plus 1 factorial. Okay, and what are the coefficient in terms of the h polynomial h vector? You have this nice combinatorial description of these one as the number of permutations in terms of this Eulerian numbers. So these are just the number of permutations of the symmetric group D plus 1, with the sigma 1 is j plus 1, and the descent number of this one is j. So this was the beginning, and then the people have worked a lot for the various subdivisions to answer such questions. So we have there is another result, okay, which give the main motivation to study these things, because they have proved more than that one, is that this h polynomial is real rooted and only simple one, which means they had no rules of multiplicity greater or equal to 2. So your polynomial is log concave and unimodal as well, and hence the Charney-Davis conjecture holds for the barycentric subdivisions of this. This is the main actually motivation to study for the various subdivisions these kind of. So one may ask that what are there the subdivisions for which the h polynomial is always real rooted. So I will talk about that question later. So here what we have done is about we have so I'm just giving here the coefficient for the h polynomial or h vector. And here we have calculated these numbers are nothing, just the sigmas, which are the not only the from the bdn plus 1, but with we are fixing the last coordinate with the positive sign. Sigma 1 is I plus 1, and this number is j. So here we can write this h polynomial in terms of these polynomials times the h vector of the original data. Okay, so using this relation and the further properties of the sequence, this sequence is actually the interlacing, as I said before. So, and if you'll consider that HIs are positive for this simplicial complex, like if you are considering the shellable simplicial simplicial complex, then this one is always real rooted, and hence we can prove that the Charner-Davis conjecture also hold for the interval subdivisions. Okay, so now so as I said that there are a lot of other well-known subdivisions. For example, RH wise subdivision. This studies phase vector study was done by the Welker and Berenti, and then Jushchenko discussed about the real rootedness of H vector. There is another partial barycentric subdivision is by Ahmed and Welker, and the antiprism subdivisions. This is just recently introduced by the Athanasias, Brunning, and Kubitschek. So now let me just if you give me, I have time, like 5 to 4 minutes, 4 to 5 minutes.
Yeah, just few minutes, few more minutes.
Yeah. Okay, just few minutes. So let me just not go in the detail of this definition. Let me just say something that what is uniform triangulation. So this definition is something which tells you about the like subdivisions or the triangulations, but it gives you, it covers lot what I have talked about the previous subdivisions, R, H, Y subdivision, interval, antiprism, and a lot of other one. They will covered in this definition. So if you will fix some non-negative integers and you have build on that one, you consider if polynomial of that triangular array, and then you just consider that if you will look locally, or you will just take the restriction of some phase on this triangulation, then you get this. If you will get the f polynomial is same as the given this f polynomial, then you will call that is a uniform one, right? And all the subdivisions which I have already described, they are all uniform one, because if you will see locally, if you will look face either face, every face has the same type of the subdivisions which we have defined. Okay, so this is the result which was by the Athanasians. That he says that you have always, if you are considering this uniform triangulation, you can always get the H vector of the triangulation in terms of the linear transformation. This is always coming from the linear transformation, and these coefficients are always non-negative integers, right? And here are a few questions. So I will just end up with these questions. So the first question is, what are the necessary and sufficient conditions for these a triangular array for which the F uniform triangulations exist? Because not for every every kind of triangular array you can find this the uniform triangulation, but for which one you need to answer this one. And there is another question, if you want to ask for every uniform triangulation, is this polynomial h polynomial of this uniform triangulation is real rooted or not? And I will at the end I will ask I will answer or the comments on this question. Brinty and Welker asked the question, if you have shellable polytopal complex, then is the f polynomial or the h polynomial of the barisecting subdivision of T real rooted or not? So here, what is known? First, about the first question, nothing is so far, but we have some examples, but we don't know what is the necessary and sufficient condition on FIs. And the second question is by the Athanasias. He answered this question partially. He has put some criteria for the subdivisions such that it becomes each polynomial becomes real rooted. And for the third question, there are a lot of classes for which this is known. For example, the cubical complexes is again by Athens Dias, and for the other classes of polytopes, was written by the Halavika and Solus recently, and these are the references for uh, things for the cubical complexes and for the other shell level complexes, shellability and the subdivisions by these Solus papers. Okay, that's what I want to say. Thanks for your attention. If you have any questions, please.
Thank you, Dr. Shaheen. Any questions from the audience?
Imran, I have a question. It's a general
Yes,
question.
Mhm.
Okay. So I've seen that you people started with this simplicial complex and then done some algebraic calculations. So is this possible that if we start with some group and then associate some simplicial complex with that, is this possible? Can we do this?
Okay, if what I have defined here, Eulerian polynomial, you can do these Eulerian polynomial for each while group of each type, right?
Okay.
And you get, okay, what is Eulerian polynomial here? Let me just connect with this one. So you know that there is, you have some simplicial complex associated to those while groups. And these Eulerian polynomial are actually the age polynomial of those simplicial complexes.
Is this something has to do with some buildings, you know, which
Yes.
are also some simplicial complexes? Okay. Okay, that's nice. Okay, thank you.
Okay, Shaheen, there is a question. If the Chana-Davis conjecture is is being satisfied, so why the people are wondering to study it further for other subdivisions or something like that? What is interesting for that?
If this is true for one of the one class of subdivisions, and we
Yeah,
need to
but
see that
for the rest of
further
the
because
cases,
it's not it's conjecture, still conjecture for the large class, which is flag simplicial homologous pairs. It's just a subclass here, which is done for that one. We need to see
okay.
further. Yeah.
Any other question? Okay. If this is the case, let us thank the speaker once again. Thank you, Shaheen, for a very nice
Thank
talk.
you.
And definitely, this is okay. There is one more question. There is one more question, which says that can you please give some application of the subdivision in real life? Actually, I'm trying to understand. Okay. Would you like to comment on this thing?
It has a
Or
lot of application, triangulations in computer algebra, computer science. You can see that the images, when you have some images, you can subdivide those images to look clearly the picture. So that's the one of the application which you can see
okay.
there.
Let me just add on one more thing. Whatever is being discussed in this particular talk, this is a topic which is in combinatorial commutative algebra as well as fall in the theoretical computer sciences. So this is a related area of theoretical computer sciences. So where people are working at, and moreover, if one is more interested to know about what is the background, what is the motivation behind the G conjecture and these things. So there is a very nice video in number file about the G conjecture, which is about the characterization of looking at the sphere in higher dimension. So the characterization of the sphere is one of the central problem in topology and topological point of view. So this is the way of characterizing the simplicial sphere by looking at the H vector. So I think Ali come up with some question. Ali, hi Ali. Ali
Hi,
Akbar.
Imran.
Hi
May I
Ali.
ask a question,
Hello.
please?
Yes, yes.
Sure. Yeah.
Hi, Shaheen. Thank you for your
Hello.
nice presentation. And it's my great pleasure that I can see you via Zoom and in this nice lecture. Well, actually, my question is somehow general. I mean, well, as much as I know, the barycentric subdivision has the same homotopy to the original complex. I mean, they have the same homology, and so when one is, for example, Cohen-Macaulay, the other is Cohen-Macaulay, and the advantage of the barycentric subdivision is that it is a flat complex, but the original complex can be the Stanley-Reisners of the original complex can be generated by variables, I mean by monomials of greater degree. So I'm wondering if it is true for any subdivision of a simplicial complex. For example, if sigma is a geometric subdivision of a simplicial complex delta, is it true that they have the same homotopy classes, and also they are homology equivalent, and also, for example, I want precisely I want to know if the interval subdivision has the same property as the barycentric subdivision.
In terms of, you are asking about in terms of these
in terms of the homotopy, in terms of homology, and being a flag complex.
It's also for flag one. It is also flag subdivision, right? And the other property, I exactly don't know because I didn't see in that way. If barycentric has this property, to either we can see for the interval subdivisions or not. So at this moment, I don't know. I must say that I don't know. I think
well,
so that has the same property, but I'm not sure.
I want to give a comment here. The advantage of studying the barycentric subdivision of a simplicial complex instead of studying the original simplicial complex is that they are homology equivalent. For example, then if the barycentric subdivision is, for example, Cohen-Macaulay, the original complex is Cohen-Macaulay. This is a good motivation to studying the barycentric subdivision complex of a simplicial complex. Is there any motivation for studying the, for example, interval subdivision of simplicial complex?
The interval subdivision has the same property if you're because this is subdivision actually. So subdivision is saying that it has the same homeomorphic structure with the original delta.
Okay. So
let me just add on.
Subdivision. So subdivision is saying that because here I have just if you look topologically, they are homeomorphic. If you consider here the interval subdivision and the original one, they are homeomorphic. Yes, that's true.
Okay, very good.
Let me add on. Let me just add on. In the case when the original simplicial complex is a simplicial sphere, then the barycentric subdivision or this subdivision, interval subdivision, does preserve the homotopy structure or topological structure. But if there are the original simplicial complex is not a homology sphere, that means it has some homology, non-zero homology at a different level. With the subdivision, I think the homology increases. We have more holes, more triangles which are not filled. So I don't believe that this is going to be. This is just my instinct. I'm not sure that I think the homology increases after the subdivision. You understand, Ali, my point?
No. Homological. I mean, he was saying a homotopy type. So because after the subdivision, this is homeomorphic to the originally equivalent. They have the same homological groups and same structure.
Yes, I believe so.